This is a unit on graph theory. It's going to be unlike anything else that you see in here because we're going to be drawing a lot of pictures. And you'll even, in one of your projects, maybe that you'll see next time, you'll actually be constructing graphs. And maybe it'll be something like, you want to visit these 10 cities in the United States. What is the shortest path that you would take to these 10 cities if you had to fly from one to the next? And you could set it up so that you want to have the cheapest flight among those cities, 10 different flights from cities to cities. Or you can think about it in terms of driving. What would be the minimum driving distance? And a couple of the problems we're going to solve here that are, unique in mathematics. One's called the traveling salesperson problem. And the traveling salesperson, it's really changed because now we call it the FedEx person or the UPS person. They drive a lot of miles in a year, and they employ some pretty significant mathematics so that when they send a driver out onto the road, that they give them the minimum distance that they should travel from all of the stops they have to make. And the math that we do here today, you'll see exactly how they solve that problem. The other one is the mail person. When they do mail routes and they drive and they deliver mail to suburban mailboxes, they want to deliver their route in the shortest amount of time, and they have to go down every street because there are houses on every street. And so the question is, if they want to do it in the least amount of time, what should their route path be so that they hit every mailbox, but they don't want to backtrack. They don't want to go down the same street twice because that's inefficient. What is the shortest path that would take them so that they hit all the streets? And that's a different problem than the second one, which is the UPS guy. He doesn't have to go down, or she doesn't have to go down all of the streets. She just has to hit all the places that are going to have a package delivered to them. And there'll be some roads out there that they don't even travel. But we'll look at how to solve problems like that using graph theory. All right, so let's take a look. The sections here, this is chapter 16, 16.1.1 and 16.1.2, and then 16.2.1. Those are the three sections that we'll do today. And then we'll do another three sections on Thursday. In the first couple of sections, you get a lot of terms. So here they are. And I call it graph theory, but it's just, I don't know that it really is a theory. A graph consists of a finite set of points called vertices, little dots. So you've got the vertices. Singular would be vertex. So one vertex, two vertices, three vertices, four vertices. And then, in addition to having a bunch of points, you have these edges that connect 2 points. So there's an edge. It's a line connecting 2 points. You can have as many edges as you want. You can even have two edges going from one vertex to the next. So there are two different edges here that go from one vertex to the next. The edges can be curvy as long as they start and they connect with another vertex. Now there's some edges that start at one vertex and finish up at the same vertex. This is a special kind of an edge. It's called a loop, but those are the three constructs that we're going to use to construct all of our graphs. And generally, we're going to want to count up the number of vertices. We're going to want to count up the number of edges. So in a graph like this one here, how many vertices are there? How many edges, and how many loops? Right, so for the vertices, we just count the number of dots. 1, 2, 3, 4. It's important to note here that it looks like these two lines here, these two edges intersect, but in fact, there is no vertex there. There's no intermediate stopping point. So think about 3D, where this edge here would be kind of underground in the tunnel, and this one here might be the bridge going over the top. but there's no vertex here. So there's 4 vertices only, A, B, C, and D. The edges, usually the way I'll count them is I'll just put a little tick mark. So I've counted AD, and then I've counted BC, and I've counted AC, and I've counted BC, and this loop over here is also an edge. So there are 1, 2, 3, 4, 5 edges. Now, this edge over here is a special kind of an edge that starts and ends at the same vertex. So we call that a loop. There's one loop. Now, we use these graphs to model certain situations, phenomena that exist out there, because if we can model a scenario with a graph, then we can use the abstract ideas of mathematics to analyze the graphs. So for example, I'm going to turn North Metroville and South Metroville into a graph. So you'll start with a picture like this, and then you want to create a graph that looks like this with edges and vertices. And here's how we're going to define this. It says draw a graph that models the layout of Metroville. So land masses, we're going to use vertices, and for bridges, we're going to use edges. So this picture is not that great, but you have 3 islands in the middle of a river here. You've got North Metroville, which is on one side of the river, and South Metroville, which is on the other side of the, all right, so here's a vertex that represents North Metroville, and here's another vertex that represents South Metroville. So here's the landmass, here's a landmass. Then we have these 3 islands, and they're islands, and so they're surrounded by water. They appear in the middle. They are other land masses. All the land masses do not have to be the same size. We have island A, island B, and island C. So we're going to label the vertices, and then we're going to look at the edges. So the edges are the bridges. So right here is a bridge connecting island A with North Metroville. So to indicate that over on the graph, we're going to connect an edge between A and M, North Metroville. They don't have to be in the same configuration. They can even be curvy. There is a bridge that connects here in the middle, island A to island B. So we're going to indicate that with an edge connecting A and B. There is another bridge here that connects island B with island A. So we're going to draw that there. I'll try to indicate the bridges here. I know the diagram's not that great. Okay, so it looks like there's only one way to get from North Metroville to South Metroville, and that way is that you have to go, into island A, then over to B, and then over to C, and then there's 2 choices to get you to South Metroville. Okay, so we have 1, 2, 3, and then we have these 2. Both of these go from island C to South Metroville, but they're on different parts of the island and different parts of South Metroville. So to indicate that, we want one edge to go from South Metroville to island C, and then we have another one going back. So there are 2 bridges. So this is the graph that would model this landmass, and that's it. So you're going to be looking at graphs like this. So I'm not sure how they're going to make you write these answers. They'll probably give you multiple choice, and they'll give you 4 or 5 different graphs, and you have to choose the right one. Now, the question we're going to ask later is then, can you walk over all the bridge without backtracking? And so, for example, if you start at North Metroville, can you go through all of the bridges without backtracking on any bridge? And we will look at some theorems that tell us, just by looking at the graph and counting up certain things, whether this can happen or not. All right, the next problem we're going to model with a graph is a map. And for this one, the vertices will be the states or the different regions. In this case, it's a subset of the of the US. So Montana is unusually close in the presidential election, but probably Trump will win Montana, Idaho, Wyoming, and Utah. I'm not sure about Utah because Mitt Romney's from Utah and he doesn't like Donald Trump and they really like Mitt Romney. Colorado is going to probably go for Biden. Not that that's relevant to this problem, but it's interesting nonetheless. Okay, the edges will be lines that will connect two states if they have a common border. All right, so we already know that since vertices are the states, and you can count in this picture 1, 2, 3, 4, 5 states. That means we're going to have 5 vertices. And I'm going to write them in the relative position to where they are. So over here, I'm going to start with Montana, and then Idaho, and then Wyoming, and then Utah, and then Colorado. 5 states, 5 vertices. Okay, next, the edges are going to be such that we're going to connect 2 vertices together. We're going to connect 2 states together if they have a common border. So let's go up to Montana. Montana has a common border with Idaho. So we're going to connect Montana to Idaho. Montana also has a common border with Wyoming, right here. So we're going to connect Montana with Wyoming as well. Let's just go through all 5 states and make sure that we have an edge connecting the state with an adjacent state that they have a common border. We know that Idaho has a common border with Montana. Here it is. Idaho also has a common border with Wyoming. Here's the border. So we're going to connect Idaho, I with W. We also see that Idaho has a common border with Utah in here. So we're going to connect Idaho with Utah. And coming then from Idaho, it has 1, 2, 3 edges coming from it. That means it's got 1, 2, 3 common borders with the 3 other states that are in this particular example. All right, let's go down to Wyoming. We've already established the edge from Montana to Wyoming and from Wyoming to Idaho, but you can see here that Wyoming has a common border with Utah, and Wyoming has a common border with Colorado. So Wyoming has to go to Utah and to Colorado. So Wyoming is kind of in the middle. It's got a common border with Montana, Idaho, Utah, and Colorado, all 4 of the other states. And so 1, 2, 3, there are 4 edges that leave Wyoming. Utah is next. It has a common border with Idaho and Wyoming, but it's also got a common border with Colorado. So we're going to connect Utah with Colorado. And then finally, Colorado has a common border with Wyoming and Utah, and we've already have those edges drawn. So here is the graph that you'd want to construct that would model this map. Let's do one last one before a break. This last one here on this page. You're going to have a floor plan, and you've got the floor plan of a house, but then you also have, you can think of the outside as being a big, outside room. And you might have several doors on your house that lead to the outside. But in this case, the floor plan, we're going to have rooms are going to be the vertices, and the doors between the rooms are going to equal the edges. So if you just go through and you count the number of doors in the floor plan, that's how many edges you have to have. And if you count the number of rooms, A, B, C, D, and then E is outside, that's treated as one big outside room, that's 5 rooms, you're going to have 5 vertices. All right, so I'm going to put my 5 rooms in here, pretty much in the same position as they are in the floor plan. A, B, C, D, and then E. E is outside. And just go from room to room and find out how many doors are attached to each room and where they're leading. You can see here that there's a door that connects room A to room B. So over here in my picture, I'm going to have an edge that connects A to B. You also see a door that takes you from room A to room C. So over in the graph, we're going to have an edge that connects vertex A with vertex C. We have 1, 2, 3, 4, 5 more doors. All right, here you see B has a door that goes to the outside, and outside is E, all of E. So we have a door going from B to E. So we'll draw that one there. Continuing along, we have a door that connects B to D. So we have an edge that connects B to D. We have a door that connects C to D. So over in our graph, we have an edge that connects C to D. All right, and then finally, it looks like we have 2 other doors that go from D out to E, but there's 2 of them. So we have to have 2 distinct edges going from D to E. Generally, I don't like to go cross through the middle of the graph. I like to go around, and so I'll put one edge there going from D to E, and maybe take another one and go back the other way. So sometimes the graph looks very little like the actual floor plan. I mean, there's not a big door that kind of goes all the way around here. So nothing is drawn to scale in these graphs. And there are many, many more ways to do it. You know, for example, you could have this one here. As long as you have the 1, 2, 3, 4, 5, 6, 7 doors, means 7 edges. 1, 2, 3, 4, 5, 6, 7. And you have 5 rooms. 1, 2, 3, 4, 5. You've got all the edges, all the vertices you need. So this graph would work. So if you're doing multiple choice items online, if the graph that you construct does not look like one of theirs, just count up the number of vertices and count up the number of edges. Make sure that there is a edge going from one edge going from B to E, one edge going from A to B, and so on. We would call these 2 graphs here equivalent graphs because they have the same number of vertices and they have the same edges going from the same beginning vertex to the ending vertex. 5 vertices, 7 edges. All right. When we come back, we'll continue with this. You're getting just a bunch of a definition and then how we use graphs to model. We will continue with this in about 10 minutes. So let's come back at, let's say, 3:55. So for example, here's one. And this one is just a bunch of streets, something that the mail carrier would need to know about. So you've got a bunch of houses. Sometimes the houses line both sides of the street, and sometimes the houses are just on one side of the street. So in this example, we're talking about a mail carrier and delivers mail to the 4-block neighborhood. 1, 2, 3, 4 blocks. She parks her truck at the intersection as shown right there in the figure, and then walks to deliver the mail to each of the houses. The streets on the outside of the neighborhood have houses on one side only, and then the streets on the inside have houses on both sides. The mail carrier must walk down just one side of the street and deliver to the mailboxes on that side of the street. So if there are homes on both sides of the street, they have to walk down one side of the street to deliver those mail to those houses, and then turn around and come back the other side of the street. All right, so to model this one, you can see draw a graph that models the streets of the neighborhood walked by the mail carrier. Use vertices to represent the street intersections and corners. And one edge if a street must be covered only once, 2 edges if the street must be covered twice. All right, so if you take this diagram here, we're going to have 3 vertices along the top at a corner, and right here is where the mail carrier is parked, and then over here. So these 3 would be these 3 here. And then in the middle, we have another intersection there, and intersection there. something like that. 3 more vertices at the intersections. And then finally down here, we also have 3, 2 and 3. So total, we have 9 different vertices because we have either corners or street intersections. All right, and then the mail carrier must deliver mail just once down the outside streets because there are houses on just the outside. But on the interior streets, you have houses on both sides. So there has to be one edge going down the north side of the street and then another edge going down the south side of the street. And so there and back, there and back, and back. So the path that the mail carrier must take could be modeled by this. All right, just want to make sure you're there and you're engaged. And so for this graph, write down the number of edges and the number of vertices and put your answer in the chat. Okay, let's see. How do you determine what to use as the vertices and the edges? A lot of times in the problem, it'll just tell you. Like this one said, let the intersections be the vertices, let the corners be vertices. So they'll tell you. And but moving forward, if you have a problem similar to these, you'll be doing them in the same way. In this one here, well, it really didn't say here what you should use as what. And so I think it would make sense. It would be hard to model the doors with a vertex. And so sometimes if it doesn't work one way, then you might want to just try it the other way. Okay, I see a lot of answers that are 9 vertices and 5 edges. And okay, so here are the vertices. So I agree with the 9 vertices because you can count these dots and there are 9 of them. But go ahead and count up the edges again because you're all off on the edges. And every time you have a curvy or a straight line segment connecting 2 of those dots there, the dots we call vertices, then you count it. So that's an edge, that's an edge, that's an edge, that's an edge, 5, 6, 7, 8. So just going around the outside, you have 8 edges. And then you've got another 1, 2, 3, 4, 5, 6, 7, 8, another 8. So if you answered 16 for the edges, you'd be correct. 16 edges and 9 vertices. Okay, now to do some of our interesting, apply some of our theorems, we're going to have to count what we call the degree at each vertex. And so I'll just use this problem right here, the degree. The degree is the number, the degree of a vertex. The degree of a vertex equals the number of edges coming into that vertex. So just count the number of edges that have come into a vertex. So here's this vertex right here. You've got this edge and this edge coming into that vertex. So we would say that the degree of that vertex right there is 2. If you go to the next one and you count the number of edges coming in, this edge comes in, this edge comes in, this one comes in, and this one comes in. There are 4 different edges that come into that vertex. So we say that the degree of that vertex is 4. Every vertex will have its own degree. And you can have multiple vertices that have the same degree, like all these ones on the corner, all have degree equal to 2. 2 edges coming in. This vertex here, you have 1, 2, 3, 4 edges coming in, 4 edges over here, and 4 edges coming in over there. So the degree of those middle intersections there are all degree 4. And then the one with the largest degree is the one in the middle because you have 1, 2, 3, 4, 5, 6, 7, 8. 8 different edges coming in there. So in several of your problems, you're actually going to be going around the graph and you're going to be counting up all of the degrees. So let me give you another example. And in this one, I will give you maybe a loop. Here's a loop. Okay. There are 3 vertices write down the degree of each one of those vertices. Yeah, thanks. Go ahead and put your answer in the chat. If you don't know, just write a question mark. I want to make sure that you're here. Okay, thank you. Here's A, and there is exactly one edge coming into A. The degree is 1. Here's vertex C. You have 2 different edges coming in there, 2. And for B, yeah, for this loop here, you actually count both of these edges coming in. So there's 1 and there's 1. So it's 1 edge connecting B with B, but yeah, we got to count 1, 2, 3, 4, and 5. So B has degree 5. Here's another one. B, A, B, C. Let's do A, B, and C. And write down the degree again of each vertex. Yeah, so A doesn't have any edges to come into it. So we would say that the degree is 0. And then C has 1, 2, 3, 4, and B has 1, 2, 3, 4. So yes, you're correct, 0, 4, and 4. Now, there's another idea coming up, but I'll illustrate it here. Most of the graphs that we've constructed were connected. And what that means is that you can get from one vertex to any other vertex, or not from any other vertex, but you can, there's a way, there's an edge that connects A to every other vertex through some kind of a path. And in this case, A is not connected to either B or C, it's disconnected from the rest of the graph. So we say that this is a disconnected graph. All of the other ones that we've done have been connected. All right, just a couple of other terms. If the degree is an odd number, like 1 or 5, we would say that these are odd vertices. And if the degree of a vertex is an even number, a mathematically even number, like 2, 4, 6, 8, and so on, we say that it's an even vertex. Everything down here is even. The other idea here is the adjacent vertices. 2 vertices are adjacent if there's an edge connecting them together, if there's at least one edge connecting them. So most of my examples here, A and B are adjacent, B and C are adjacent. But A and C are not adjacent because there's no edge connecting A and C. Adjacent means next to, immediately next to. So B and C are adjacent because there's at least one edge connecting them, and A and B are adjacent, but A and C are not. Lots of terms today. All right, still working on terms, and we're going to use them in the future sections. And now we have a path. A path is a collection of vertices and edges that indicates well, the easiest way to define it is a path. You just travel along a route from one vertex to the next until you stop. And where you stop is where the path ends. And so here is an example of a path. And if the path starts at vertex A, you can see it's drawn here, we would indicate the path by writing A first. And then you go from A to B through these arrows. So this is the first edge traveled. And then we go from B to C. That's the second edge that's traveled. And then we go from D to E, A, B, oops, D. There's no C in there. And then from D to E. And here's the path. There's lots of paths that you can construct. If the path starts and ends at the same vertex, we call it a circuit. So if we did A, B, D, E, if we started off in the same way, and we went A, B, D, E, and then we continued, and we went back up to B, so that was the fourth edge, and then we went back to A. If we start and end at the same vertex, that's called a circuit. And all circuits are paths. Circuits just have that one additional edge that takes you back home. Start at A, end at A. All right, let's take a look at some, we have everything that we need. Let's work on some examples. I'll give you a chance to try these, and then We'll go through the answers. Are these two graphs equivalent? There's two graphs. It's not one graph. This is not one disconnected graph. This is two different graphs. All right, so graph 1, graph 2, and then graph 3. Now graph 3 you have to construct, and so we know these two are equivalent. So draw a third graph that's equivalent to the first two. Graphs that are equivalent have to have the same number of vertices. So you can see both of those first two graphs have the same vertices, but also have to have the same edges. So I'm going to go through and I'm going to write down all the edges here. You've got edge AB, you've got edge AD, you've got edge AC, you've got edge BC, you've got edge BD. 1, 2, 3, 4, 5. 5 different edges, and there they are. Now, if you can confirm, the graph can look much, much different, but if you can confirm the second graph has the same 4 vertices and the same 5 edges, then we say that the two graphs are equivalent, no matter what they look like. So vertices, you can see that we have the same 4 vertices, A, B, C, D. And for the edges, all right, I'm just going to write them all down. We have AD, that one there. We have BD, that's this one here. This one up here is AC. By the way, AC and CA are the same, but I'm just writing them in the order that they come in the alphabet so that I can compare the two different graphs. All right, what else? We have AB here, and we have BC here. And if you compare those 5 vertices with those 5, you'll see, or edges, I mean, you'll see that they're exactly the same. AD, BD, AC, AB, BC, they're all there. All right. Okay, so let me give you a different graph. How about A, B, C, D. Nothing about these two graphs in terms of where the vertices are located looks rectangular like this. Okay, draw graph 3 that begins this way, but it must be equivalent to these two. Equivalent. We can see already that we have the same 4 vertices. Now we have to have the same 5 edges. So you have to construct in your graph a graph that has these 5 edges. So you can just go ahead and go through each one of them. AD, okay, there it is. BD, right there. AC, yeah, I'll go around this way. AC, AB, which is right here, and then BC, which is right here. So notice my graph looks quite different than those other two graphs, but all 3 of those graphs are equivalent because they have the same vertices and they have the same edges. So equivalent is equal in quotes, right? All right, you can see some of these examples that here would be an example over here where we model a town where the land masses are vertices and the bridges are edges. Here's the example where we have a floor plan. And here's an example where we have the male person going up and down these streets. So model it with a graph. All right, let's go down to this last one here. Go through this entire, count up the number of edges, count up the number of vertices, count up the number of loops, count up, and then go through each vertex and write the degree next to each vertex. Identify the number of even vertices, identify the number of odd vertices. So basically they give you a graph like this and they ask you to go through all the definitions. Okay, do the vertices first. Just quickly go through it and just write a number next to each vertex indicating the degree. Like, so for example, at A, you'd say, there's two edges that go into A, so the degree is 2. So just write a 2 next to, or some other number next to each vertex. And put one in the chat. D, what's the degree of D? Vertex D, okay? Good, 3. And as before, if you don't know, then put a question mark. And if we've got a bunch of question marks, I'll spend more time on it. All right, 2, that one's 3, that one's 1, this one's 3, 2, 2, 2. What did you find for C? 1, 2, 3, 4, yep, 5. The loop counts as 2 because it leaves the vertex and then comes back to the vertex. And it's counted as 2 in terms of the degree. All right, so we did number 34. Using some definitions, which of those vertices, itemize them, A, C, and D, or which ones are adjacent to E. So which vertices are adjacent to E? And remember, adjacent means that there's an edge containing E in another vertex. Okay, yep, that's right. Just D, here's E by itself there, and there's a edge connecting E with D, but there's no edge connecting E with any other vertex. So only D is adjacent to E. Okay, use vertices to describe 2 paths. I'll give you one and then you give me the other that start at vertex A and end at F. So here's my path. I'm going to go A to C, and then I'm going to go around the loop to hit C again, and then I'm going to go to D, and then I'm going to go to F. Give me another path from A to F. A, B, C, C, D, F. Yep, that's another one. A, B, C, D, F is another one. Yep. Okay, so all of those that you've identified are correct. 40, it says use vertices to describe a circuit. Now remember, in a circuit, you have to start and end at the same vertex. And they tell you that it begins and ends at F. So you're going to have F, something in the middle, and then F again. And here's F. You have to be able to come back to it. So there's really, one of 2 choices there. F, I, H, G, F, going around the clockwise, or going around counterclockwise, but you must start and end right there at F. So F, I, H, G, and then return to F, or go the other way, F, G, H, I, and then back to F. So one of those 2 would work. And sometimes they get really, really specific, like number 42. Use vertices, like we have here, just list them in order based on the way you would traverse the path. From vertex H, here's H, to vertex E, here's E, passing through I, but not G. So they give you a lot of details here, so maybe there's just one single path that you can use here. All right, from H, so you start at H, and then you need to come over here to E. Can't go through G, but you must go through I. You can't come down here, so it must be I, F, D, E. And it's just a path, it's not a circuit, so you're not going to return back. And generally with these paths, we don't want to backtrack. Then they ask you some explaining questions. Why isn't A, C, D, E, D not a path? All right, so A, C, D, E, and then back to D. So the reason why this is not a path, because backtracking is not allowed. A, C, D, G, A, C, D, G, A, C, D. Okay, there is no direct edge from D to G. You'd have to first go through F if you wanted there to be a path. So no edge between D and G. Oh, I can see that there's one concept here that I didn't define, and that's a bridge. A bridge in the graphical sense. A bridge is an edge. It's an edge that if you removed it from the graph, you would create a disconnected graph. Okay, so what are the bridges? If we remove the edge GH, just got rid of that edge right there, the graph would still be connected. You could find a path from any one vertex to any other vertex. Same thing for IH or IF or GH or FG. DF is a bridge, because if that edge was not there, then there would be this component of the graph, And then there would be this connected component, but they wouldn't be connected because the edge DF would not be there. So if you remove an edge, and by doing so, you create a disconnected graph, then we say that the edge that you removed is a bridge. Do you see another bridge in there? And give me just the beginning and the ending vertex of your edge. Yeah, I see CD. CD is another one. Because if you remove CD so that that edge was not there, then you'd create two components, this connected component over here and this connected component over here, but they are not joined together. There would be no way to get from, say, A to H. No way to get from one connected component to the other connected component. A bridge just has to disconnect the existing graph. So this whole thing is a graph, and if we take out an edge and create two components, then the edge we removed is a bridge. It's kind of like a what if. If you remove this edge, then you would create a disconnected graph. Yes, and the last one is DE. Now this one's a little subtler, right? Because if you remove DE, the first component that's disconnected would be just the vertex E, because the vertex E would have nowhere to go to any of the other vertices if you remove DE. The other connected component would be everything else except E. So it's a bridge, even if when you remove it, you create a disconnected graph that consists of only one vertex. All right, so there's a lot of terms in this section, and we've defined them all. And so when we go to the next section, we're going to use some of these definitions to answer some interesting, or just observe some interesting relationships. So this loop goes from C to C. If we remove that edge, it's really a loop, but if we remove it, the whole graph is still connected. It didn't create two components such that you couldn't get from one to the next via a path. All right, so this next section, as you can see, is 16.2.1, and this is all about Euler graphs, Eulerian graphs. Euler is a German name. It kind of looks like the Mount Pleasant mascot, the Oilers. Euler was a German mathematician, very prolific. He wrote on all kinds of math topics. In the last part of his life, he was blind, and he did some of his best work when he was blind. You'll see his work in all different branches of mathematics. So we're going to define, we already know what paths are, paths. We're going to have a special kind of path, and it's going to be called an Euler path. And an Euler path is a path that travels through every single edge of the graph with no backtracking. You need to be able to start at one vertex and traverse the entire graph without lifting your pencil from the paper. And in the process, you have to hit every single edge. You may have had some problems that you've worked on in school at some point when they said, draw, can you traverse every edge of this graph without lifting your pencil from the paper? If so, you have an Euler path. And then a circuit is the same thing, but you traverse every path, but you start and you end at the same place. Here's one. See if you can do it. Start somewhere, start at one of the vertices, and then traverse the graph so that you have crossed every edge. You see 5 vertices in this graph. 1, 2, 3, 4, 5, 6, 7, 8. 8 edges. Okay, so I claim you can do it. I claim you can do it. Go through every edge, all 8. So why don't you write the path? You have to go through every edge. So I think you're going to have 8 different letters written in a row. Now you can revisit a vertex. You just can't revisit an edge. If you revisit an edge, then that means you're backtracking. Now, after we discuss this theorem here, everybody's going to be able to do it instantly. And here it is. This is just one of them that would work. So I'm just going to go here, 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 there, 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 and there. So I did the whole graph without lifting my pencil from the paper. I did revisit vertex C 4 times. So what? That doesn't matter. You just can't backtrack on the edges. And if you can do that, it's called an Euler path. If you start and finish at the same place, it's called an Euler circuit. Now, in order to know how to traverse a path like this, the first thing we're going to do is we're going to identify the degree of every vertex. So as before, vertex A, there are 2 edges coming into it, so its degree is 2. C, 1, 2, 3, 4. B, 1, 2, 3, 4. So the degree is 4 there as well. Those are even vertices. But down here at the bottom, E and D, they each have a degree of 3. So we have 2 odd vertices, and we have 3 even vertices. Turns out that the oddness or the evenness of the vertices instructs us as to how we do this. Now, generally, if you want to traverse every edge, if you come into an edge and it's not the ending and you still have more edges to go, then you have to leave that edge. So you come in 1, you leave 2. Because you come in and you leave 2, most of the vertices have to be even. So you can come in and then you can leave. Come in come in with this edge and then you leave, except the starting and the ending point. When you start, you leave. If you return to that edge, you have to have one go to it and then leave again. But the beginning and the ending vertex of your path might be odd, but all of the ones in between have to be even. So if you went around and you identified the degree of each one of these vertices and you noticed that D has odd degree and E had odd degree, you know that the starting point has to be either D or E. If you started at B, A, or C, you would never find a path, an Euler path, if you started at one of these points up here. Because there are 2 odd vertices, you must start at one and end at the other. All right, so what do you know about this one here? Does this one have an Euler path? It's one of the examples we used earlier on today. And what we would say here is that this one does not have an Euler path. And the reason it doesn't is because we have 3 vertices out here that have degree 1. The most we can have is 2. We could have 1 to start the path and 1 to end the path. But you can't have 3 because then you have too many start, end places. And so this one's not going to have an Euler path. Too many odd vertices. See, if you start at A and you leave there, then if you go to C, there's no way to leave C. Well, let's say that you're going to have C be your end. Well, you still have G down here. So once you get to G, there's no leaving G. So you're stuck. What about this one? Here you have degree 1, and here you have degree 1. Here you have degree 3. Here you have 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. Just writing down the degrees of all of these. And all you have to do is count odd vertices. If you see more than, if you see more than 2, then there's no path. You can try all day and you'll never be able to traverse the entire graph without backtracking. So this one is got 3 odd vertices, and that means no Euler path. All right, so here is Euler's theorem, and we kind of went through some examples, but here it's stated formally. And this is for connected graphs. If a graph has exactly 2 odd vertices, then there's at least 1 Euler path, but no Euler circuit. Anything that has an odd vertex, there's no, you're either going to start there or end there. And if you start there and you're not going to end there, then there's no circuit. Each Euler path must start at one of the odd vertices and end at the other. So this is what we looked at earlier. A graph that has no odd vertices, that means they're all even. If that happens, then you do indeed have an Euler circuit. Might not be easy to find, but you do have an Euler circuit. And if a graph has more than 2 odd vertices, which was the case in the previous 2 examples that we did, then there's going to be no Euler path and no Euler circuit. So here's the theorem, and the theorem is related to identifying the degree at each vertex. And then there's this thing called Fleury's algorithm. It's kind of an algorithm that tells you how to trace the graph. It doesn't always work, however, but let's just go through it and see if it works on one of these. So the first thing I'm going to do on graph number 8 here is I'm going to write down the degree of all the vertices. You'll notice that there are 5 vertices. 3 of them are even, the ones that are either 2s or 4s. And there are 2 vertices that are odd. 3 edges coming into this vertex and just one over here. So the first thing we know is that there is no Euler circuit, because in order to have an Euler circuit, and that means start at one place and end at that same place, same vertex, all of the degrees have to be even. And we do have some odd vertices, so there's no Euler circuit here. Now, because there's exactly 2 odd vertices, there is an Euler path. So we know that there's an Euler path here. So explain why the graph has at least one Euler path, and that's because it has exactly 2 odd vertices. All right, let's use trial and error or Fleury's algorithm to find one such path. We know we have to start at either C or A, because those are the 2 with the odd vertices. We must start at 1. Let's say we start at C, and let's end at A. All right, let's go ahead and read this and see if we can follow the instructions to get the Euler path. If the graph has exactly 2 odd vertices and therefore an Euler path, choose one of the odd vertices as the starting point. All right, we did that. If the graph has no odd vertices, therefore an Euler circuit, you can choose any vertex as your starting point. All right, this one doesn't have any Euler circuits, but it does have an Euler path. All right, number the edges as you trace through the graph according to the following rules. After you've traveled over an edge, erase it. And that's because you must travel each edge exactly once. So you erase it. I'm not going to erase it, but maybe I'll cross it out. Show erased edges as dashed lines. When faced with a choice of edges to trace, choose the edge that is not a bridge, and go over a bridge if there's just no alternatives. Okay, remember, if you take out a bridge, you create a disconnected graph. All right, so we're going to go here. I'm just going to color with a different color, and I'm going to label that number 1. So that's my first edge. And now I have 3 different choices from here. I can go down BE, or the other BE, or BA. So you have a choice. So I'm just going to go here. This is not a bridge, so I can traverse it. 2. Then I'm going to come back up. I'll put arrows on these too so you can see the direction. Then I'm going to come back up to B here, keeping in mind all along that I have to finish at A. So then I'm up here. There's only one place to go from here, and that's over to A. So there's 4, my 4th edge. And then I'll come back down here. That's my 5th edge. And then there's only one path to take me home. And that's back this way, edge 6, and then back here where we end. And we have traversed all of the edges. They're all shaded in green now. And once you see all the arrows, then you would identify the path according to the vertices that you crossed or you connected. So we're going to start at C, and then we went to B, and then we went to E, and then we went back up to B, and then over to A, and then back down to E, and then over to D, and then up to B. So here's the Euler path. Notice that it doesn't start and end at the same place. So therefore, it's not a circuit. So this whole section is about Euler graphs, and you're going to see a large variety of them. So why don't we just take a look at these 4 and just identify it as Euler path, Euler circuit, both, neither. Whenever a problem talks about Euler, you need to write down the degrees, because to determine whether you have an Euler path or an Euler circuit, it has something to do with the degrees. All even vertices, there's a circuit. Exactly 2 odd vertices, there's a path but not a circuit. More than 3 or more than 2 odd vertices, 3 or more, there's neither a path, Euler path, or an Euler circuit. So it looks something like this. Degree 2, degree 2, degree 3. Degree 3, degree 2, degree 2. Exactly 2 odd vertices. So there's an Euler path, but no Euler circuit. This one here, degree 2, degree 2, 1, 2, 3, 4, 5, 6, degree 6, degree 2, degree 2, degree 2. And this one, you have all evens, all even vertices. So because there are all even vertices, there is an Euler path and there's also an Euler circuit. And if there is an Euler circuit, you can start anywhere. And wherever you start, that's where you're going to end, because that's the definition of a circuit. You must begin and end at the same place.